In this video we're going to talk about linear velocity and angular velocity, the second two topics of Standard 3. And I want to start this just with posing a question. So I have young children and they always like to compete against me. They like to play board games or card games, and they like to race me as well. And so for a while, as a parent, you kind of maybe let them win. So if I'm running a race against them, I might kind of not really run very fast so that it's at least kind of a competitive race. But it doesn't take them long to figure out that, I'm not trying all that hard. So suppose I wanted to run a race against my kids who, are significantly slower than I am. But I want them to see me trying really hard, and I want us to be able to have the same starting line and the same finishing line. So how could I do that? One way I could do this, if I thought that maybe we could run a race on a circular track, would be for us to start in the same place and end in the same place. So maybe over here in kind of standard position is my starting line for both of us. And then we'll finish here as well. But how about I run on an outside track and they run on an inside track? Okay. So let's think if we did that, then let's say, my kids have gone a little while and I've gone a little while to where we've traced out the same angle. Okay, I've clearly covered a larger distance than they have. Okay, so while they wouldn't take them long to figure out this isn't a fair race, they would be able to see me putting forth kind of my maximum amount of effort, and yet we would still kind of stay a lot nearer each other because of the fact that they just don't have to cover as much distance to cover the same angle as me, right? And so when we both get back to the finish line, we've both covered an angle of 2 pi in radians, or 360 degrees, and we end up at the same spot, but I have clearly covered a lot more distance. So what this leads us to is understanding that when I'm looking at how fast each of us are going, there's kind of two aspects to it. There's this idea of how much or how many radians, for example, we're covering in a given amount of time. And then there's this aspect of how much actual distance in feet or inches or meters or whatever that we're covering in a given amount of time. So when we're talking about movement along a circle, there's two types of velocity. There's angular velocity and linear velocity. Okay, so as a point moves along a circle of radius r, we say that its angular velocity is given by this symbol here. I know it looks just like a W. It's actually the Greek letter omega. But of course, as you're doing your work, if you write W, that's fine. And it's just theta divided by time, right? How many radians do you cover in a given amount of time? And then linear velocity would just be the arc length covered in a given amount of time. Okay, so we'll use this omega for angular velocity and v for linear velocity. So let's say that we're both keeping pace with each other along this line, and as we go, this line just sweeps out, and we kind of keep these relative positions to one another. We would say that our angular velocities are the same, right? Omega are the same for both of those, but the linear velocities are different. All right, so let's take a look at an example here. So this one has to do with the clock Big Ben in the Parliament in London. It has a very large minute hand. Its minute hand is 14 feet long. And so part A asks us to find the angular velocity of the minute hand of Big Ben in radians per minute. Okay, so we know that our angular velocity is just given to us by theta over time. All right, so let's think about, kind of a convenient amount of time. We want radians per minute, but it might make sense to think about, once around the clock. If we go once around the clock, then we know that that'll take 60 minutes, of course, right? But how many radians do we cover in those 60 minutes? Well, okay, if we go once around the clock, we know one revolution is 2 pi radians. So our angular velocity here, we can do a little bit of simplifying, turn that into 30. And what we get, of course, is pi over 30. And technically, radians are unitless, but I think in the case of angular velocity, it's nice to just go ahead and say radians per minute. It's kind of awkward to just say per minute. So pi over 3 radians per minute. And then, this is a kind of a real-life problem here. So let's go ahead and give the approximation to that. I get about 0.105 radians per minute. All right, so there's my angular velocity. All right, now let's talk about the linear velocity of, and I kind of messed up my sentence here, of specifically the minute hand of Big Ben. As we were talking about in the first one, that's what I intend for us to answer in part B here. So what is the linear velocity? So in other words, if I was a bird that perched on the end of the minute hand of Big Ben, how fast would I be moving if the clock just kind of had continuous movement? Okay. Well, we know that linear velocity is arc length, right, over time. Okay. But let's keep in mind here, what is the arc length in this situation? Well, in any situation, it's the radius times the angle theta, right? And, well, we already figured out theta over t up here. We found that was pi over 30 radians per minute. So maybe I'll just separate these out real quick. And then I can just specifically say, all right, this is r, which is 14 feet. And then theta over t, which, by the way, is just my angular velocity, is pi over 30. And I suppose I could do a little bit of reducing, not much. So this is 7 pi over 15. And let's think about what the units are, okay? 14 is in feet. And then the pi over 30 is in radians per minute. So this should be feet per minute. Okay. Now let's stop for a second. 7 pi over 15 feet per minute. Okay, we might want to get an approximation here, but let's notice what it asked for, right? It asked for inches per minute, so I'm not quite done yet. So what I want to do here is remind you of your ability to do unit conversion factors, right? Depending upon how much chemistry, physics, things like that you've done recently. You might have various levels of comfort with doing unit conversions, but this is a very important skill to have. So let's review it here. If I want inches instead of feet, then I can multiply by a fraction that I don't want it to change my answer, right? I don't want it to change it, but I want it to look different. So instead of feet, I want it to be in inches. All right, so the idea is I can cancel feet out from the numerator here if I put feet in the denominator here. And then I really want inches in place of feet, so if I put inches in the numerator, then that'll do that trick for me. But then I need this fraction to just be 1, and so I need to make sure that my number of feet on bottom is equivalent to my number of inches on top. So if I multiply by 12 over 1, I of course get this converted into the units I want, which is inches per minute. So I cancel my feet. Oops. Cancel out the feet. And so now I've got the units that I desire. So I go 7 pi times 12 divided by 15. And let me just calculate that. So I get about 17.6. 17.6 inches per minute. All right. So that gives us the answer for both of our questions. But I want to do one more thing before we leave this problem behind. I want you to notice what happened right here. When we realized that we already knew theta over t, because we computed in the previous problem, we separated out the r from the theta. And so this thing, right, as I mentioned, is the angular velocity. So notice that if I take radius times angular velocity, what's that equivalent to? That's equivalent to my linear velocity. So on the next page, this kind of gives us our last formula that we want to be able to be conversant with. We have that linear velocity can always be found by taking the radius times angular velocity. And so you can see the derivation here. It's basically the same thing that I did on the previous page. So let's do one more example here. It says a typical tire for a compact car is 22 inches in diameter. If the car is traveling at a speed of 60 miles per hour, find the number of revolutions the tire makes per minute. So first of all, let's just understand, a lot of times a really nice place to start with the story problem is to just understand what the units are of the answer that's being requested. So they want the answer, right, to be in revolutions per minute. Okay, but what's a revolution, right? It's once around the circle, right? So we understand that that's equal to 2 pi radians. So when they say revolutions per minute, let's just understand that they are asking, right? They're asking for angular velocity. Okay, because you know we worked with radians per minute or radians per any unit of time in our previous example, but this is also angular velocity, just as expressed in different units. So that's what we're shooting for here. Okay, so we know from the previous slide that linear velocity is equal to r times angular velocity. Okay, so this is what we want, right? We want that. And I suppose they give us diameter, but you know we can find the radius pretty easily from the diameter. So my question is, do we know v? Okay. Well, the answer is yes, right? The car traveling at a speed of 60 miles per hour means that our linear velocity is also 60 miles per hour. So in other words, if we paint a little dot on the edge of our tire, then if the car travels 60 miles in 1 hour, then that dot will form an arc length of 60 miles in 1 hour as well. All right, so we know V and we know R. So of course I can take this formula, I can manipulate it and understand that really what I'm going to use here is omega equals V over R. Okay. So let's keep in mind, I want to get revolutions per minute, right? And I have velocity in miles per hour. My radius here, I know that that is, let me list it over here actually, 11 inches, cutting the diameter in half. And V is 60 miles per hour. So let's understand first of all that I can't just plug 60 and 11 in over here, right? Because the units are not matching up. Okay, I have inches here, I have miles here. I want those units to be the same. So I either need to convert inches to miles or miles to inches. Now, a good rule of thumb is to always make your conversion to go from a bigger unit to a smaller unit. So in other words, turn your miles into inches. And the reason for that is so that you end up multiplying instead of dividing, right? So you're going to generally have a lot nicer numbers to work with. So I want my 60 miles per hour to change. I'm going to do that right here, 60 miles per hour. And I want to get that into inches. Now the most natural conversion here is not directly to inches. It would be to say there's 5,280 feet in 1 mile. But I understand that that didn't quite do the trick for me, right? I need to also get my feet to inches, okay? But I can do that with, there are 12 inches in 1 foot. And then my feet cancel. But let's also understand that right now I'm in hours, right? And what do I eventually want? I eventually want to be in minutes, right? Because I want revolutions per minute. So let's go ahead and make that conversion here as well. So I know that 1 hour is equal to 60 minutes. And so then I can get my hours to cancel, and notice that the only units to kind of survive that whole process are the inches on top and the minutes on bottom. Now you can see that there's some really nice canceling that can be done here, right? My 60 and my 60 cancel, so that's rather nice. If that didn't happen, if it doesn't work out to a nice whole number, then just keep the fraction so that you're not rounding in the middle of a problem. But in this case, we're rather fortunate. So what we end up with is 63,360 inches per minute. And this, right, we started with 60 miles per hour. This is my linear velocity. Okay, so I can plug this in over here. So omega is equal to, and I'm going to go ahead and keep the units. It's generally wise in these problems to keep your units in there to make sure that in the end you have the units you want. So there's my V, and then my R is 11 inches, so I'm going to divide by 11 inches. But I know that if I take this fraction divided by 11 inches, that's the same as 63,360 inches per minute times the reciprocal of that, so times 1 over 11 inches. So I get these inches to cancel out, okay? And it shouldn't be surprising that the only unit that survived here is the minutes on the bottom, because remember, omega is an angular velocity. So if I have no units up here, then that means what I really have are radians, right? So when I divide 63,360 by 11, I actually get another nice number, 5,760. And again, radians are unitless, but I think it's helpful to just go ahead and write radians per minute here. All right, so I've gotten myself an angular velocity. But let's remember how they asked for the answer. They wanted revolutions per minute, not radians per minute. So I'm not quite done. So my last order of business is to get myself into radians per minute. Or sorry, excuse me, get myself from radians per minute into revolutions per minute. So we have omega is 5,760 radians per minute. But what I can do is I can get this into revolutions per minute, just like I converted my miles per hour into inches per minute. I can use a unit conversion factor. And so I've got radians that I want to cancel out, even though it's not technically a unit, and I want revolutions to appear on top. And so let's think about 1 revolution is equal to 2 pi radians. So with that, I get the radians canceling out, I get revolutions appearing. So my angular velocity here is 5,760 over 2 pi revolutions per minute, right? But that's not the nicest way to write an answer like this. Let's just get the approximation. So my approximation here would be 916.7 revolutions per minute.